Alright, so today we are looking at, I guess it's called the hausdorff series, this chapter. We're continuing on with our discussion of this whole thing here. Sorry my chair is being loud because it's in the wrong spot. So we start out with a set of two elements. Two indeterminates, say u and v, be a set. And definition. The element h corresponding to our old u. It's kind of like a fake addition with v, which was log of the exponential of u times the exponential of b. Because keep in mind, this is, under normal conditions, this would be like equivalent to addition under like the mapping it to the multiplicative space with the exponential map and then mapping it back. And the idea is that we don't necessarily have a like group function, action, whatever on our space, so we can use this to build one that should work like addition. This of the Lie algebra. This is our L hat from before over the rationals free over our two item set is called the hausdorff. Hausdorff series in the indeterminates u and v. We denote by hn, alternatively hr comma s, the homogeneous component of h of total degree n or alternatively multi-degree Rs and so then we can write h as the sum of these hn for non-negative n, or as the sum of these r comma s for non-negative r and s. And we can write hn as the sum of r and s, of h of r and s, for of course r and s, once again positive, and r plus s equaling n. This brings us to our theorem. First theorem states if r and s are positive integers such that r plus s is non-zero, it has to be at least 2, right? Then h of r and s is equal to h of r and s prime plus h of r and s double prime, where r plus s times h prime of r comma s So we can get this by dividing by that r plus s is the sum over positive m for negative 1 to the m minus 1 over m, and then the sum for the sum of Ri being from 1 to m being r. I should actually write out with the indices. So R1 through Rm being equal to r, you have S1 plus through the Sm minus 1 being equal to S minus 1. And you have 1 plus S minus 1. You have R1, I'm guessing. They mess up the formatting. Plus S1. You have R1. Yeah, you have R1 plus S1. Sorry, I'm figuring out how to write this as I'm writing it. Being at least 1 through Rm minus 1 plus Sm minus 1 being at least 1. And this is then over the product from I is 1 to m minus 1 of the adjoint of u to the power of Ri over Ri factorial times the adjoint of v to the Si over Si factorial times the adjoint, all that times the adjoint of u to the Rm over Rm factorial. All of this whole big thing acting on v. We similarly have r plus s times h double prime of r comma s as the sum is again m we're at least 1 minus 1 to the m minus 1 over m. The sum of this time it's r1 through rm minus 1 equaling r minus 1. You have the sum of s1 through sm minus 1 equaling s. And you have r1 plus s1 being at least 1 through rm minus 1 plus sm minus 1 being at least 1. And this time it's a bit simpler, our inner term. It's the product from 1 to m minus 1 of Ri copies of the adjoint of u over Ri factorial times Si copies of the adjoint of v over Si factorial, all acting on u. On the proof, in the rational Magnus algebra on two indeterminates, exponential of u times on the exponential of v is equal to 1 plus w, where Rw is the sum from r plus s being at least 1 of u to the r over r factorial times v to the s over s factorial. So we have that h is the sum for m at least 1 of negative 1 to the m minus 1 of wm over m that is h of r comma s is the sum for positive 1, negative 1 to the m minus 1 over m of the sum for r1 plus through rm being equal to r, s1 plus through sm being equal to s, and each ri plus si, at least one, of the product from I equals 1 to m of u to the ri over ri factorial, v to the si over si factorial, the linear mapping Pn where Pn of xi of x1 through xn is 1 over n times the product from 1 to n minus 1 of our adjoints, of course, of xi acting on xn for n at least 1, and of course each xi in u and v. This map is a projector of the nth of the rational free associative algebra in two indeterminates onto the same component of the free rational Lie algebra in two indeterminates. And as hr comma s belongs to L rational r plus s in two indeterminates, h r comma s is stable, is unchanged by the function of p of r plus s. Now we get p of r plus s on the product from 1 to m u to the ri over ri factorial, v to the si over si factorial is 1 over r plus s. I'm going to do what they did above and just write this over on the left hand side. So, because I think this is going to be a long term here on the right, this is the product from I equals 1 to m minus 1 of adjoint of u ri over ri factorial, adjoint of v si to the si over si factorial, the adjoint of u to the rm over rm factorial, the adjoint of v to the sm minus 1 over sm factorial acting on our final v. This is when we have v's at the end, and if we don't, then we have to tear off a u to act on instead. And so our new function looks similar. But now it just is going to end a bit different. Once again, I equals 1 to m minus 1. The adjoint of u to the ri of ri factorial. This inner term stays the same, because this is all just stuff we're leaving alone. And then this time it ends in the u's and we're tearing off one to act on. So we get the adjoint of u to the rm minus 1 over rm factorial. Now acting on u, when sm equals 0, which gives us, of course, rm is, we want to be at least 1. Now, clearly, the adjoint of t, p minus 1 times on t is 0 if p is at least 2, and the null and like the 0 adjoints of t on t is t. Thus, our first equation up there, that's our first case for r plus s, p r. Our first case for r of s, p of r plus s is 0 when s of m is at least 2, and our second of that form is 0 when the exponents of the u are at least 2. So in both cases, when our last exponent is at least 2, it's going to zero out. The theorem follows as h prime rs is the sum of terms of the first type and h double prime of r plus s is sum of terms of the second type. Some remarks to follow that. So yesterday we defined a projector Q of AX of the free associative algebra on X onto the free Lie algebra of X, such that Q of our a to the m is 0, 0 for a in our free, and essentially in the copy of our free Lie algebra in AX, and m being at least 2. and that q of 1 is 0. Then h is q of the exponential function of h is q of the exponential function of u on the exponential function of v, giving us h of r and s is q of v to the r over r factorial times v to the s over s factorial. For number 2, we just have that h. I should write this out on a new line, this whole thing. H of u and v is u plus v plus 1/2 of u on v plus 1/12 of u on u on v plus 1/12 of v on u minus 1/24 of u on v on u on v. I'll write it like this, then we have terms of at least order 5. They'd write it as like modulo L5, same thing. I want to specify here these are higher terms. Alright. Part 3. HO of n equals hn of 0 is 0 for n integer not 1. So h of u and 0 is equal to h of o and 0 and u, which is u, as the bracket of u and negative u is 0 by linearity and alternativity, I think is the word for it. We get that h of u and negative u is equal to 0, as it should be. Next, we have substitutions. In the Hausdorff series. As K is containing rationals as a field, the Hausdorff series can be considered as a Lie formal power series over k with coefficients in Rk. So if G is a complete Hausdorff filtered Lie algebra with G as the union of our positive G alphas, it's unreadable, G alpha we can substitute some A and B and G for our U and V and H. So, to be more particular, let A be complete Hausdorff filtered Lie algebra. Nope. Filtered. I skipped forward. Hausdorff filtered unital associative algebra. We write M as the union of positive A alphas and M alpha as the intersection of A alpha and AM and M for real R, for real alpha, so that M alpha equals A alpha if alpha is positive, and M alpha equals M if alpha is non-positive. We define our bracket in the way you'd expect. With this, M is a complete Hausdorff filtered Lie algebra. Alright. Let's get a proposition. For A and B and M, the exponential of the Hausdorff of A and B is the exponential of A on the exponential of B. So, proof. There exists, we can find essentially an A alpha that contains both A and B. Then there exists a continuous homomorphism of the Magnus algebra in two indeterminates into Ra mapping U to A and U to A and V to B. Then the restriction of theta to L hat of U and V is a continuous homomorphism of our L, U, and V, L freely algebra indeterminates into Rm mapping U alternatively V to A alternatively B. Then, by an old formula, we have theta of H is H of A and B. Applying theta to the formula at the exponential of H of U and V. Let's try again. Of H of U and V is a exponential of U and exponential of V, and that is everything. Now we have a remark. If A and B commute, then H RS of A and B is 0 for R plus S being at least 2. As every homogeneous Lie polynomial of degree at least 2 is 0 at A and B. Then H of A and B is A plus B, and we get the exponential of A plus B is the exponential of A times the exponential of B. Alright. Bring this to our next proposition. Let G be a complete hausdorff filtered Lie algebra such that G is the union for positive alpha of G alpha. The mapping of A and B to their Hausdorff is a group law on G compatible with its topology. With identity 0 and inverse A being sent to negative A. In the proof, we know that the Hausdorff mapping here and the negative map are continuous. So we only need to show that our group law here is associative, that it has an inverse, has a unit, a two-sided identity that is, not a unit, and that it has inverses. We can assume, we can take A, B, and C indeterminates in G being the L hat of A over indeterminates A, B, and C. The restriction of the exponential map to RG is an injection into the Magnus algebra and we can just calculate all the above, where exponential of h of A and B. I just don't need brackets between the exponential and its what it's acting on. Try to keep things cleaner. The left version of the associativeness is exponential of h of A and B on the exponential of C. The exponential of A on the exponential of B times the exponential of C. Which exponential of h and A on h of B and C, exponential of A on the exponential of h of B and C, which is the above, obviously, in the easy manner. The exponential of h, A and 0 is the exponential of A on the exponential of 0, which is the exponential of A, and likewise the exponential of h and 0 on A is the exponential of 0 times the exponential of A, which is the same as the above. And the exponential of h of A and negative A is the exponential of A on the exponential of negative A is the exponential of A minus A is the exponential of 0, which gives our relations. remarks. Would they start numbering at 2? Take our group to be the Lie algebra L hat of X. Our 2 group laws on this coincide. As in A weird H of B is H of A and B. Thus, the Hausdorff group law is given by the Hausdorff series. Secondly, let G be a Lie algebra with lower central series as an integral filtration. Suppose we have M at least 1 such that the mth central series of G is 0. With the filtration topology, that's what I'm going to call it, it's the topology of the filtration. G is Hausdorff complete and in fact discrete. And then P of A1 through AR is 0. For every homogeneous Lie polynomial of degree at least m. Thus, our HR of S of A and B is 0 for R plus S being at least M. And then our series H and B as the sum over R and S of HR S of A and B has cofinitely 0 terms. As a series that's cofinitely 0. Then our group law is a polynomial mapping. Let's do a proposition. Let K sub R and S be the component of H of U plus V and negative U of multi-degree R and S. Then K and 1 of U and V, the n plus 1th component on U and V is 1 over n plus 1 factorial of U copies of the adjoint of n copies of the adjoint of U acting on V. Proof. I want to write K of U and V being H of U and V, H of U plus V minus U, and K1 of U and V being the sum for positive n of K n comma 1 of U and V. We denote by L, or alternatively R, as left and right multiplication by U on a hat of U and V on the Magnus algebra. Then the conjugate of V by e to the U is the sum over P and Q of e to the P over P factorial V, of course, negative U to the Q over Q factorial, which is equal to the sum for n at least 0, 1 over n factorial times the sum for P plus Q equals n of n factorial over P factorial Q factorial of L to the P minus R to the Q on V, which is the sum for positive n, non-negative n of 1 over n factorial times L minus R to the n acting on V, giving us that our conjugate of V by e to the U is the sum over positive n of 1 over n, non-negative n over 1 over n factorial times U adjoint, n adjoints of U acting on V. Oh, sorry, one second. We now calculate under the modulus of the ideal of the sum for positive m, the sum for n at least 2, non-negative m and n at least 2 of a to the m comma n. 1 second. A of m comma n of U and V of the free associative algebra of U and V. For all n at least one, we get that u plus v to the n is congruent to u to the n plus the sum from 1 to n minus 1 of u to the I, v, u to the n minus 1 minus I. So the adjoint of u on u plus v to the n is congruent to left multiplication by u minus right multiplication by u of the sum from 1 to n minus 1 li, the rn minus I, acting on v, is congruent by L to the n minus R to the n on V, which is congruent to U to the n times V minus V U to the n. So by summing over the n, we get that the adjoint of U on e to the u plus v is congruent to e to the u on v minus v e to the u. And we also note that k1 of u comma v is congruent to k of u comma v, and that e to the k1 of u comma v is then congruent to 1 plus k1 of u comma v. So k1 is congruent to e to the k minus 1, which is congruent to e to the u plus v e to the minus u minus 1. Thus, we get that the adjoint of u, I need to write this better, the adjoint of u on k1 is congruent to u times e to the u plus v e to the minus u minus e to the u plus v e to the minus v of u, which is congruent to u to the u times e to the u plus v minus e to the u plus v times u, all this times e to the negative u, which is congruent, we've seen, to e to the u times v minus v e to the u times e to the negative u, which is congruent to the conjugate of v by e to the u minus v, which is congruent to the sum for n at least 1 of 1 over n factorial positive n factorial times the n copies of the adjoint of u acting on v, which is the adjoint of u acting on the sum for non-negative n of n copies of the adjoint of u over n plus 1 factorial acting on v, which by our previous result gives us our proposition. Now after this, we're going to look at convergence of the Hausdorff series first off in the real and complex space, and then moving on to the I believe we're moving on to the p-adic. I don't know if that's even how you say that. In that case, and then I think we're on to Humphreys. So yeah, we're getting there. I look forward to that. I don't know what's happening to my voice here.